We've talked before about the fact this debate over is light a wave or a particle, and eventually people realized that it's neither. It kind of acts like each one at a different time. Nobody had ever really had this idea about molecules or atoms or electrons, protons, anything like that. It was just commonly accepted those things were particles. A physicist named Louis de Broglie came up with the idea that just like light has a wavelength associated with it, maybe matter does too. This brings Planck's constant in again, and just as a sort of a hint, whenever you see Planck's constant, you're going to be talking about some kind of quantum mechanical phenomenon. So, what de Broglie suggested for this wavelength of matter is the wavelength should be h, Planck's constant, divided by p, the momentum of the particle. He says this is true even for macroscopic objects, but there's no way for a macroscopic object to interact with things that are around its wavelength. We can do some math and see. Baseball has a mass of 0.15 kilograms, so it's not very big. And if we throw it at 1 meter per second, very, very slow, the wavelength associated with it, we put in the numbers and do the math here, is 4.4 times 10 to the negative 33 meters, which is just impossibly small. Uh, it's about this is about 10 to the negative 18 times the size of a proton, so a billionth of a proton. And a proton is about a billionth of a kilometer. So we're talking about a ridiculously small size. So that wavelength means nothing to a baseball that's a few centimeters in size. If we make this bigger, if we make it a larger mass or make it move faster, this wavelength will just get smaller. It'll make it even harder to see anything. The only way we can get anything experimentally useful out of this is to go to very, very small objects. So, for example, if we have a proton and we accelerate it through a potential difference of 1,000 volts, we can solve for its velocity. This is a problem we would have seen at the very beginning of the course. Charge of the proton times the voltage difference times 2 divided by its mass. The square root of that is the velocity. We're just saying Q times delta V equals kinetic energy. We get about 440 kilometers a second, which is pretty fast, but it's well below the speed of light, so we don't have to worry about relativity. We can keep sticking with Newtonian physics. What is its momentum? Well, we multiply mass times velocity, and we get this very small number. We plug it into lambda over h over p, and now we get a wavelength of 9 times 10 to the negative 13 meters. This is a large wavelength compared to the size of the proton. So the proton could go through a hole this size, for example. With electrons, it's even more dramatic because they seem to be point particles. What that means is, like mathematical points, they have zero size, which sounds crazy. We know they have charge, we know they have mass, and they interact and all that. But to the best of anyone's ability to determine, there is no physical size there. So they are, essentially infinitely small. Uh, One of the things that we'll see here soon is if we wanted to make a really good microscope with visible light, there's a limit to how good it could be, and what it boils down to is the wavelength of the light we use is our sort of fundamental limit for how small of an object can we see. If we use light with a smaller wavelength, like X-rays or gamma rays, that would seem like we could make a better microscope out of that because now we can see things that are their size, their wavelength size, so nanometers or less. The problem is we can't really make a lens for X-rays or gamma rays like we can with visible light because the lens is made up of atoms, and these wavelengths for X-rays, this is around the size of an atom, so we can't make a lens. Electrons, on the other hand, we can focus. We can bend their paths with a magnetic field. This is what makes the electron microscope such a big deal, and it can see individual atoms because electrons have this wave nature. They can be focused with magnetic fields, and we can make a microscope. Now, because matter has this wave-like characteristic, the things that you saw in the interference and diffraction chapters apply to matter as well. people have done double slit interference experiments with electrons and even larger things. I think somebody did them with carbon 60 things known as buckyballs. Um, the weird thing about this brings us to the uncertainty principle, and this is part of physics that Einstein could not accept, and it's weird to believe that there's something that he was mentally stuck on, but he could not accept the idea of quantum mechanics, and the reason is back before Einstein, before quantum mechanics, physics was thought to be deterministic. So nothing in the universe is really random. It just is a reflection of your lack of knowledge. So, for example, if you knew exactly how hard somebody's thumb was going to hit a coin, and exactly where on the coin, and what was the mass distribution of the coin, the air pressure, all that other stuff, coin flips wouldn't be random to you anymore. You could calculate, oh, that one's going to land heads, that one's going to land tails, whatever. It would be a horrible problem to do mathematically, but you'd get it right every time if you did it right. Same idea with any random process like rolling dice or roulette or whatever. One of the interesting ideas from centuries ago, they don't mean a computer in the electronic sense that we're familiar with, but if you had the ability to calculate, if you could know the position and momentum of every particle in the universe just once at the same time, which again, it sounds like a lot to ask, and it is, but if you could know it just once, then you'd know all there is to know about the future and the past. How did the universe begin? How will it end? Lottery numbers, who's going to win the Super Bowl? All that stuff would be determined according to this belief that physics was deterministic. Now, of course, we don't have any way to get all those measurements, and we don't have a computer that could make it work, but it's just an interesting idea in principle. It turns out it's not possible even in principle. No matter how much we spend on better instruments, we can't get the exact position and momentum of even one particle one time, much less all the particles. With what we know about physics now, we don't expect this to ever change, even with future improvements in equipment, because it seems like no particle has both a perfectly defined position and a perfectly defined momentum at the same time. So this is another crazy idea from modern physics. This is called the Heisenberg uncertainty principle, and we can say it reasonably simply. If we talk about the uncertainty of measurement of a particle's position as delta x, and the uncertainty of measurement of its momentum at the same time as delta p, what we'll find is the product of those uncertainties is always greater than or equal to Planck's constant over 4 pi. Now remember, this delta x, this uncertainty, is the same thing if you were measuring something with a meter stick. You might say your uncertainty is, half a millimeter. That's your delta x. But what this is telling us is no matter what equipment you use, fancy national lab equipment, you measure delta x, delta p of one particle at the same time, the product will always be greater than this. So you can't get the exact, you can't get zeros for both of these things. You might see this written a little bit differently because h over pi or 2 pi or whatever comes up a lot. And just to make life easy, physicists have defined h bar as h over 2 pi. So if we use that, we would say uncertainty in position and momentum, their product is greater than or equal to h bar over 2. So this is telling us if we make a better measurement of position, we're going to lose our ability to measure the particle's momentum. One way to explain this is to say if we want to know a particle's location, we have to bounce light off of it. We have to look at it. And if we use light of a particular wavelength lambda, we're not going to know its position to any better than about lambda. That's going to be our uncertainty. So delta x here is, we use the little tilde because it's approximately lambda. However, when the photon hits the particle so that we can see it, it's going to deliver some of its momentum to the particle. We don't know how much, if it'll be almost all of it or almost none of it. So our uncertainty in momentum is at least the size of the photon's momentum. We already know what the photon's momentum is, right? It's h over lambda. So the uncertainty in the particle's momentum is at least that big. So now if we multiply our delta P and our delta X, we get H, which is greater than H over 4 pi. So if we use a longer wavelength photon so that we don't hit it as hard, we don't screw up the momentum measurement as much, it means we won't know the position as well. There is more than just this one uncertainty relation in quantum mechanics. The only other one we're going to care about connects energy and time. So quick explanation of this that doesn't require quantum. Let's say you're at a gym, you're supposed to be keeping track of your heart rate and you're trying to measure your pulse. You might count the beats for 10 seconds and then multiply by 6 to get your pulse. What this means is you can't measure a pulse of 75 beats per minute because that's not a multiple of 6. What if you count for 30 seconds and multiply by 2? You'll get a better answer, but now you can't have any odd number for your pulse. You'll be within plus or minus 1 beat per minute, but let's say you want to do better. Let's say we count for a full minute, and we can say, okay, now we have the exact answer. It's so many beats per minute. If we assume your pulse is constant for your entire life, just to make life easier, maybe the real answer would be something like 75.2 beats per minute. So now you have to count for 5 minutes and divide the result by 5 to get your accurate pulse. And you can see what this means as this number gets more and more, we get more and more digits for it. We have to count longer and longer. So the quantum mechanical version of this is if we want to know the energy of a particle very precisely, if we want to make delta E, the uncertainty in energy, small, then delta T is going to be large. This means the lifetime of the state will have to be very long if we want to measure its energy. What we mean by lifetime, we'll see in the next chapter, or you might have seen in chemistry. If an electron gets bumped out of the ground state up to a higher energy state, it wants to drop back down. And the only way to do that is to get rid of some energy. It usually does this by emitting a photon. The time the electron spends in that higher level is called the lifetime of the excited state. That's our delta T. And it tells us if the electron is only in that higher state for a small amount of time, it limits how well we can know the energy, because a small delta T necessarily means a big delta E. This uncertainty principle thing will let us explain a lot of different weird results in physics. It lets us figure out the size of a hydrogen atom. Why does double slit interference work like it does? It's really a pretty neat idea.